essentially I'm taking the line integral on the boundary of the following linear combination: minus t dx plus f dy. All right? I didn't do anything rather than switch the order between these two and rewrite it in a clear form, which is exactly the one over there. The one over there, line integral, is supposed to be a function dx, then a function dy. All right? Okay? So this minus t plays around with the same function f over there. And f is exactly the function t over there. All right? Now with me? So this is actually my f over here, where f is the t over here. So I can still use Green's formula right in this board, which is exactly saying I need to take the double integral of a scalar function. Double integral of the scalar function, the x derivative is hitting on this function. All right? And minus the y derivative is hitting on this function. Okay? So in the end, I have a double integral partial f partial x plus partial g partial y dA, which is exactly equal to the double integral of the interior with respect to divergence. Okay, so now we have slightly two different Green's theorem. On one hand, okay, on one hand, if I'm taking the line integral on the boundary in the form of f dx plus g dy, I'm getting a double integral of the interior where the integrating function is the curl of the function. If I'm taking a line integral on the boundary with the representation f dy minus g dx, I'm getting a double integral in the interior with respect to divergence of the function. Okay? So the same function, the same vector field. The double integral in the interior, one is with respect to curl, the other one is with respect to divergence. Then it is going to be equal to the line integral on the boundary, but with different representations here. Okay? Again, you might ask, what the heck is this? Right? Why are we interested in this? What is divergence telling me? So the easiest representation or explanation you can use, which I prefer very much, you can also go back and compare it with the original form of Green's theorem, is the following. This representation is not a very arbitrary, it's actually a very special combination. Okay? This combination is nothing but the line integral on the boundary, a vector field dot with the normal vector dx. Which in this case, I'm taking the inner product between the vector field with the tangent vector. Where here, I'm taking the inner product between the vector field and the normal vector. Okay? So one is about the circulation and the work you've done along the curve. The other one is a completely different animal. Okay? So if this is my curve, again, if I have a lot of small arrows upon anything, any point on the boundary, so if I'm taking the line integral along the boundary with respect to the inner product between the vector field and the tangent vector, I'm actually following this curve for a whole circle and see how much work I have done following this force. Okay? But if I'm taking the inner product between these two, the vector field and the normal vector, if you think about what it means for the inner product between a vector field, so this is a vector field, this is a normal vector. Okay? So if you can imagine there is a flow happening in R2. So there's a water or any fluid. So they are flowing around in R2. And the direction and the magnitude of a vector field is defining where this water is flowing towards and how fast it is flowing towards. Okay, so if you have a fluid flowing around an R2, and they are flowing depending on the vector field you are given, And then I use a closed curve to bound a particular region and see how much fluid is coming out of this closed curve. Can you understand what the problem is? So imagine there's a lot of fluid floating around on R2. And I choose a closed curve to bound a particular region. So in some places, I have a direction and magnitude of the water is going towards. And if I have a normal vector, the dot product is actually talking about how fast and how much of fluid is coming out at this particular point. Now with me? How much fluid is actually coming from this particular point? Imagine if your fluid is flowing exactly at the same direction as the normal vector. This is coming out fast. It is, of course, also depending on the magnitude of this vector field. Now with me? If this vector field is actually pointing inwards, where the normal vector is always pointing outwards. If this happens, the vector field at this particular point is pointing inwards of the closed curve, where the normal vector is pointing outwards. The inner product between these two is actually negative. All right? The inner product is the magnitude product multiplied by cosine of the angle. If the angle is between 0 and pi half, you get a positive. If the angle is between pi half and pi, which is exactly what happened here, then the inner product is actually negative. Negative is talking about the fluid is not coming out, it's actually going in. Okay? And if this vector field is orthogonal to the tangent to the normal vector, so let's see where I have the example. Let's draw a different one. So if this is my vector field, it is exactly orthogonal to the normal vector at this particular point. So in a small scale, in a very small scale, at this particular point, the fluid is neither coming in or going out. Okay, so we don't have any contribution. So this overall line integral along the boundary, where you're taking the inner product between the vector field and the normal vector, is talking about overall how much fluid is coming out, how much fluid is going in. Okay, so that's the explanation of why this particular representation is very interesting. Okay, if I have this explanation, but how is it related to a divergence of the vector field? Okay, so this can be mostly easily understand in the following way. So if the divergence of the vector field is equal to 0, if this is the case, then we say F is incompressible. And in the textbook, they call it a source free, which is probably more trivial to understand. Okay? Here is this relation between the line integral on the boundary and the double integral of the divergence in the interior. Divergence of the vector field is actually talking about whether this point can suck in fluids or flow out fluid. You know what I mean? So for instance, if I'm taking the integral on the boundary, okay, if the integral on the boundary of this particular inner product between the vector field and normal vector is positive, that is actually talking about there must be something in the interior coming out. Okay? If your fluid is incompressible, there's no way you can have the same amount of, okay, there's a better explanation. So if this is a fluid, more things are coming out than things are going in. That means there's a source in the interior. All right? If more things are coming out than things are coming in, there's a source in the interior. If there are more things going in than things coming out, then there must be a sink in the interior. Am I right? There must be a sink to suck all the fluid in. If the divergence is equal to 0, the double integral in the interior is always equal to 0. You know what I mean? Double integral in the interior is always equal to 0, which means if you take the inner product between these two and do the line integral on the boundary, it's always equal to 0. In other words, regardless of what shape of a closed curve is, the fluid coming out of the closed curve is always equal to the fluid going into the closed curve. You know what I mean? This can only happen if your fluid is incompressible. Okay? If a fluid can be compressed, then you can have more things going in than things going out. Okay? If a fluid can be stretched, it can also happen. Okay? So incompressible means you cannot compress your fluid So you give any closed curve, you take the line integral, you look at the things going out and things coming in. These two quantities have to be equal simultaneously for any closed curve. And source free is pretty much talking about the same thing. But the reason I don't quite like this is source free, you have to also require to be sink free, right? So a source is generally talking about this particular point that can provide more fluid. Again, I'm only giving a very rough explanation of what this quantity is about. But bottom line is they are interesting from a very practical point of view, and that's why maybe the physics department or engineering department requires the mathematics department to teach these kind of things. Okay? So regardless, let's just concentrate on how we can compute things, right? So in the final unit test, they're not going to ask you what it means for a fluid to be incompressible. Usually, they will say a fluid is incompressible. Then you have to translate it into a mathematical form, which is basically saying the divergence is equal to 0. Okay? So next, let's compute a couple of examples. So if I have my vector field is given by 12x squared, 11y squared. I want to compute the line integral on the boundary f dy minus g dx. Okay, remember, this representation has to be a very particular form in order to make it equal to the fluid flux relation. Okay, where C is a closed curve. C is the boundary of. So in order to save me some time, I'm just going to draw the picture. And this is the question. Okay. So this is the boundary of this region. It's basically the upper half disk, the upper half disk. And of course, oriented in the counterclockwise orientation. Okay, counterclockwise orientation. So imagine if I want to do this line integral on the boundary. I still have to divide the boundary into two pieces, the linear piece and the circular piece, right? I have to find the parametric equation for both of them, and I have to plug in the formula and see what they are. However, with this Green's formula in hand, we can significantly simplify this one, because now our favorite object is double integral. In the second chapter, you might hate double integral, but in the third chapter, double integral becomes our best friend. Now I want to do this double integral. This is half of a disk. I immediately know I'm going to use polar coordinates, right? But one thing I want to mention, so this line integral on the boundary is sometimes it's called a flux. What is it called? Outward flux. Yeah. Outward flux. Okay, which is basically the same thing as what I was saying. So if you combine all the things together, you take the fluid coming out of the closed curve minus the fluid divide going into the closed curve. This is going to be overall the outward flux, which is probably a nicer terminology. Okay, but regardless, this is just equal to the double integral in the interior divergence of the function. Okay, divergence of the function is going to be partial f partial x plus partial g partial y. Okay, dA. Okay. So quickly, if I want to have curve in a double integral, what kind of combination should I have? If I want to have curve in the double integral, I want to have f dx plus g dy, right? So that's the easiest one. So if you have an easy representation in the line integral part, you have to remember a particular combination in the double integral. If your double integral is in the easiest form, which is the divergence, then you have to remember a particular representation in the line integral part. Okay, so one way or the other. Okay, so here I have to have f dy minus g dx. Then I end up with a very nice combination of the divergence. If I have f dx g dy, then I have a symmetric difference of the differentiation of the functions. Okay, So here, as long as I'm using the upper half disk, now we're pretty smooth about setting up the polar coordinates. I want to have an angle from 0 to pi, the distance radius from 0 to 1. And partial f partial x is equal to 24x. So 24x plus 12y. And I have r dr d theta, right? Right? Remember, there is an extra factor coming out. So 24x plus 24y, unfortunately, this is not in the form of x squared plus y squared, but it's not that scary here. From 0 to 1, 24x is just 24 r cosine theta, all right? 22y is 22 r sine theta, r dr d theta.
You wrote 2 pi for the upper limit.
Oh, sorry, it's supposed to be 0 to pi. Okay. Again, if you look at this integral, r and theta are totally separated. Okay. So I can have from 0 to pi. What do we have? 20. So we can have sine theta plus cosine theta d theta. Oh, not really. I have to be a little careful here. So what we have here is from 0 to pi, from 0 to 1, 24 cosine theta r squared d theta dr d theta. Right? That's what we have right here. Second part is from 0 to pi, from 0 to 1, 22 sine theta r squared dr d theta. Both of them are pretty straightforward to compute, okay, because they are separated. R squared evaluated from 0 to 1, I'm going to get a 1/3. Multiply by 24, I got an 8. And then integral of cosine theta from 0 to pi is equal to 0. So the first contribution is actually equal to 0. All right? Yeah. Second part, I have integral from 0 to 1 multiplied by, of r squared, I got 1/3. And then 22 divided by 3, that's the contribution from